It's a pleasure to be here at Café Scientifique, and I'll be talking to you about some changes in the modern metric system. As you heard, I'm at the National Institute of Standards and Technology. Along with the University of Maryland, we have a joint quantum institute that I am part of, and I'm also a member of the laser cooling and trapping group. The group leader, Gretchen Campbell, along with Paul Lett, Trey Porto, Ian Spielman, Ida Tietzinga, Charles Clark, and Nicole Younger-Halpern are the permanent members of that group, and it's a great pleasure and honor for me to work with them on a daily basis. What I'm going to be talking to you about, the reform of the modern metric system, is something that NIST, an agency of the United States government, has been a key player in. The International Union of Pure and Applied Physics, IUPAP, has also been a continuing advocate of the International System of Units, the modern metric system. And as a member of the relevant commission of that body, I've been spreading the word about this this quantum reform of the metric system. And one of the key features of that reform is that the definition of the kilogram has changed, and this has captured the attention of a lot of the media who have talked about this. But I'd like to start at the very beginning. Here we are in a Café Scientifique, and some people have said science is about what you can measure, that if you can't measure it, it's not really science. Well, leaving apart the philosophical implications of that, it's pretty clear that if we are going to measure things, and if we're going to express the results of those measurements, we have to have a system of units. And the international scientific community has agreed upon what is informally called the metric system of units, and more formally, it's known as the International System of Units, or the Système International d'Unité, hence the abbreviation, the SI. Now, the metric system itself came into being with the French Revolution at the end of the 18th century. And what I'm here to tell you about this evening is that on the 20th of May, 2019, not so long ago, which is World Metrology Day, by the way, we have experienced the greatest revolution in measurement since the French Revolution. And that revolution to the International System of Units has to do with the way in which we understand what are the base units. All of the things that we measure in the metric system, in the SI, are based on 7 base units: the kilogram for mass, the meter for length, the second for time, the ampere for electric current, the Kelvin for temperature, the mole for amount of substance, and the candela for luminous intensity. And the revolution that has happened is that every one of those quantities is now defined by fixing the value of some constant of nature. Now, in order to see what this means and how it can be done, I'm going to begin by telling you about how an early unit of measurement, namely time, has evolved over time. And so, with apologies to the late, great Stephen Hawking, I'm going to bring you my version of a brief history of time. So, what is a second? Well, since perhaps not exactly the beginning of time, but for a very long time, a second has been a certain fraction of a day. A day has 24 hours, an hour has 60 minutes, a minute has 60 seconds. And so a second is one day divided by 86,400. Now, the trouble is, or one of the troubles is, that since around the turn of the century, we have known that the length of the day is not constant. All kinds of things can change the rotation of the Earth. The tides create a frictional force that slows down the rotation of the Earth. Earthquakes redistribute the mass and change the rotation rate. Changes of ocean currents change the angular momentum of the Earth. And so the rotation rate has to change in order to compensate for that. One of the ways in which we know that, the Earth's rotation rate changes is because we have clocks that are better than the Earth. Here's a picture of the very first atomic clock. It was actually a molecular clock. It used molecular ammonia as the ticker of this clock, and this shows a photograph of that first atomic clock from 1949. And a clock like this is better, more stable than the Earth, because it's not subject to all the kinds of things that might change the rotation rate of the Earth. A few years later, a different kind of atomic clock was built at the National Physical Laboratory, sort of the sister agency to NIST in the United Kingdom. In 1955, Perry and Essen made this first cesium clock, and around 1967, the international community agreed to redefine the second, the unit of time, in terms of the ticking of cesium atoms. Now, how does that work? Well, here is a very oversimplified version of how an atomic clock works. Imagine I've got an atom, and in the case of cesium, there's one valence electron, and there's a nucleus, and both the electron and the nucleus are like little magnets. So there's a difference in the energy depending upon whether the spin of the electron is pointing in the same direction as the spin of the nucleus or pointing in the opposite direction. What you do is you shine in microwaves at about 9.2 gigahertz, which corresponds to the energy difference between the two different directions in which the electron can be pointing. And if the frequency is just right, namely if it's this frequency, then it'll cause the electron to flip its spin. The energy of the atom will change. And if it's not the right frequency, then nothing will happen to the atom. So the way an atomic clock works is you adjust the frequency of the microwaves until the atom's electron flips its spin, and then you know that the frequency of the microwaves is this number. Because by international agreement, we've decided that this is the frequency of that transition. And you see, if we know what the frequency is, then you just have to count, 9 billion so-and-so cycles of that frequency, and that's equal to 1 second. So that's the oversimplified version of how an atomic clock works. And this is the current definition of the second, that the second is the duration of a certain number of periods, 9 billion, 192 million, and so on, periods of the radiation, the microwaves, that corresponds to the transition between these two energy levels of cesium. And ever since there have been cesium clocks, they've been getting better and better. So back here when Perry and Essen made their first clock, it was good to about a part in 10 to the 11. Well, that sounds pretty good. That's a part in 100 billion. But we're never satisfied. So people kept working on these clocks, and they kept getting better and better and better, about a factor of 10 every decade or so. They got to a little bit better than a part in 10 to the 14th by about the middle of the 1990s. But the performance of these clocks was in fact stalled at that level, at about a little bit better than a part in 10 to the 14, mainly because of the fact that the cesium atoms are moving so fast. In order to make an atomic clock, you've got to have the atoms in a gaseous form, so they're floating freely in space and not being perturbed by surfaces or other atoms. And in order to do that, you have to heat the cesium atoms up a little bit. And so the cesium atoms are moving with a thermal velocity that's more than 100 meters per second. It's not so easy to measure the ticking of a clock that is moving faster than 100 meters per second. And so we developed at NIST, in the laser cooling and trapping group, we developed methods for cooling atoms, especially cesium atoms, down to temperatures on the order of 1/1,000,000th of a degree above absolute zero. And this allowed atomic clocks to get even better. So with the advent of laser cooling that could make these atoms move not at 100 meters per second, but at less than 1 centimeter per second, these clocks got better so that they're now operating at close to a part in 10 to the 16. Here's a picture of one of those clocks. This is the people who made this clock, Don Meekoff and Steve Jeffords, laser cool a gas of cesium atoms down here, shoot them up in a vacuum about 1 meter high. They fall back down after about a second. And with the atoms going this slowly and having an observation time so long, these clocks are good to a few parts in 10 to the 16. So you see what has happened is that over time, we've gone from defining the second based on the rotation of the Earth. There's nothing special about the Earth, and except for the fact that we live there, and nothing guarantees that the rotation rate of the Earth is going to stay constant, and it doesn't. We changed from that definition, which was not really satisfactory, to a definition that is based on an atom. And as far as we know, every cesium atom in the universe is the same, and the properties of the cesium atoms are stable over time and over space, so that they make an ideal reference for a time standard. So this is a very important development, that as we go from something that doesn't have anything really fundamental and special about it to something that is enshrined in an immutable feature of nature, namely the energy levels of an atom. Now, at the end of this talk, we're going to have time for questions, and I hope you're thinking of questions. And this slide is to give you a chance to think about some other kinds of questions, maybe looking at these sample questions. You may think of some of your own, and we can address those at the end of this talk. So let's keep going. An even better story, a short history of length. Time was really important historically. People needed to understand about time for, especially on a yearly basis, to know about things like planting crops. But length was really important because it involved things like commerce, buying fabric, for example. It involved construction, building buildings. And the earliest standards of length were based on the human body. So a cubit was the distance between your elbow and your fingertips. A yard was the distance between the center of your body, your nose, and your fingertips. A fathom was your wingspan. A foot was a foot. This was wonderful because it meant that you always had the standard of length with you, but it wasn't very consistent. If you were buying fabric from a short fabric merchant, you might not get what you expected in the length of the fabric. And if you moved from one village to another, the standard of length would be different, because different people would be selling similar kinds of goods. Well, how do you address this problem? Well, the ancient Egyptians addressed this problem by saying that the cubit was the length of the pharaoh's forearm, not just anybody's forearm, but the pharaoh's forearm. And well, the pharaoh wasn't always around when you needed to make a measurement, and so they made a stone artifact, a representation of what became known as the royal cubit. And this was used in the building of the pyramids. The people out in the field who were constructing these amazing edifices used a wooden standard, which they had to calibrate against the stone standard once a month, and the failure to do the calibration was punishable by death. So these people were really serious about metrology, and the results were astounding. The pyramids baselines are consistent to a small fraction of a percent. They're square to 12 arc seconds. They really knew what they were doing. And the idea of having artifacts like this stone representation of the royal cubit was something that was common throughout Europe much later. People had such artifacts. Typically, they would vary from town to town. Here is a photograph of the standard fathom in the city of Regensburg. And as you can see, this tourist has a wingspan considerably shorter than this fathom, which tells you this might be a really good place to buy fabric. But if you were to go into the towns surrounding Regensburg in Bavaria, you would have a completely different standard of length. Well, this was a really annoying kind of problem, but it was a common problem. And the French revolutionaries figured they were going to fix it. They came up with the idea of having a new standard of length, which they called the meter. And they were going to base it on something that they felt was both unchanging and available to everyone, namely the size of the Earth. The meter of the French Revolution was supposed to be 1/10 millionth of the distance along the meridian going from the North Pole to the equator along the meridian that passes through Paris. And so during the time of the French Revolution, they sent out surveyors to survey some fraction of this meridian and extrapolated it to the full meridian from the pole to the equator. And this was to be the measure of all things. It was supposed to be good for all time and for all people. And this coin, which was struck in honor of this idea, shows a mythological creature measuring the Earth, because that's exactly what they did. They measured the Earth. And after a few years of doing this surveying work, these astronomers, surveyors came back and presented their results. But of course, you couldn't very easily check it again. And so they did something that is very much akin to what the ancient Egyptians did. They made an artifact. Here's a picture of a meter bar. End to end, this thing is the length of the meter that the French surveyors determined by surveying the distance between Dunkirk and Barcelona. And that's a picture of the meter that was deposited in the archives of France in 1799 and became the standard of length for the entire country. Well, some decades later, there was an international gathering, and in 1875, they signed the Treaty of the Meter, the Convention du Mètre, and they mandated that a new meter should be made. And here's a picture of what that meter looks like. It's a little bit more stiff because of the way it's constructed than the original meter of the archives, which you can see here. But it was made so that the distance between two scratches on this meter bar was as close as they could make it to the end-to-end length of this meter of the archives. So that was wonderful. This became the standard for the entire world. The United States had a copy of this meter bar, and we used that, as did other countries, as the standard of length for our nation. Now, the trouble was that almost as soon as this meter bar was made, it became evident that there were better ways of measuring length. In the 19th century, especially in France, people had discovered that light was a wave, that it had a certain wavelength, and they made devices called interferometers. And here's a schematic diagram of one of those interferometers, the kind that Michelson invented. You have a source of light. It goes through a beam splitter, which sends some of the light over to this mirror and transmits some of the light to this mirror. And the light gets reflected from those mirrors and recombined so that it interferes. These two paths, the one going to this mirror and the one going to that mirror, interfere, which means that some places the crests of the two waves of light add up and make a bright place. And in other places, the crest of one wave corresponds to the trough of another, and they cancel each other out, and you get a dark spot. And here is a picture of the kind of what we call interferogram that you get when you interfere these two beams of light. And the wonderful thing is that this central spot can change from dark to light by moving this mirror just 1/4 of a wavelength of light. In other words, a few hundred nanometers, a few hundred billionths of a meter. Now, the scratch on the meter bar is tens of micrometers in width, and you have to find out where the center of that is. That's not very easy to do. But here on this interferometer, you can easily see a change that is a small fraction of a millionth of a meter. And so eventually, it took a while, but in 1960, they redefined what was meant by a meter to be a certain number of wavelengths of light from this lamp, which had krypton gas in it. It made a nice orange color, and the wavelength of that color was the thing that was used to define the meter. 1960. That was the year that the laser was invented. Here's a picture of a helium neon laser whose wavelength is stabilized to a transition in a gas of molecular iodine. And pretty soon people found that these lasers were far better than the krypton lamps that's shown here. The purity of the light from these lasers was so much better than the purity of the light from these krypton lamps that soon they became the standard of length, the de facto standard of length, and everybody referenced their measurements of length to these lasers. And so it was obvious that you needed a new definition of the meter, just as when interferometry showed that you could measure things better using interference of light. Now it was clear that you could do all those interference measurements better using a laser instead of a lamp. So the obvious thing would have been to define the meter, to redefine the meter in terms of the wavelength of this particular laser. But fortunately, people did not do the obvious thing. They did something far more brilliant. They defined the speed of light. Now, how does that give you a meter? The definition of the meter was, and still is, that it's the length of path traveled by light during a time interval of 1/299 million, whatever. And that means that this number right here has now been defined to be the speed of light, because we've used the speed of light to define what we mean by a meter. And what it means is, if I've got light and I can measure the frequency of the light, and I've defined what the speed of light is, then I immediately know its wavelength. And by the mid-1980s, people had learned how to measure the frequency of light, and so they changed the definition of the meter to be this definition, which is effectively defining the speed of light. Now, the beauty of this is that you don't specify any particular source of light, any particular laser or lamp. You just rely on the fact that you've defined the speed of light, you've fixed its value, and that you've got this equation that relates the wavelength to the speed of light through the frequency, and you can measure the frequency. So any light for which you can measure the frequency immediately gives you a ruler. And if people learn new techniques for measuring the frequency of the light, and they did, and if people develop new techniques for making better light sources, and they did, then those improvements are already incorporated into this beautiful definition. And here are two of the people, Jan Hall and Ted Hench, who got a Nobel Prize for developing those better lasers and those better techniques for measuring the frequency. So something wonderful has happened. We went from an artifact, a bar that was kept in a vault outside of Paris as the definition of the meter, to a particular atom, krypton, that produced light of a certain wavelength. And then finally, to defining a fundamental constant of nature. Now, the beauty of this is that we should never need to change the definition again. All of the improvements that we hope happen in the future, that have been happening all along, are already incorporated into this new definition. That's what I call the beautiful definition of a unit. Now, by the early 21st century, it was clear that we needed to do the same thing for the kilogram. We wanted to bring this beautiful approach to defining what we mean by a unit of measure to the kilogram. And we've also done it for the ampere, the Kelvin, and the mole. Why did we have to do that, and how was it done? Well, before I go on to that, which I will in just a moment, I want to propose to you a few more possible questions that might get you thinking about other questions that you're interested in. But let's return to the question: why did we need to change the definition of the kilogram, and how was it done? And for that, I'm going to give you a light history of mass. Well, as with so many other things, we begin with artifacts. Here's a set of stones from ancient Babylonia that were the mass standards for that empire. And it had the same problem that all such artifact standards have, that as you go from one place to another, you're going to find a different set of artifacts, and the standards of mass are going to be different. So the French revolutionaries figured they would take care of that, and they would take care of it by using the meter, the thing that they had decided was going to be the measure of all things. They decided that if you made a cube of water 1/10 of a meter on a side, we call that a liter, that the mass of that water is going to be defined to be this new unit of mass called a kilogram. And so that became the new standard of mass, the amount of water that's equal to 1 cubic decimeter, or 1 liter. Now, the problem is that while this is wonderful in the sense that it refers to a commonly available substance whose properties, as long as you control the temperature, you should know pretty well, it wasn't that easy to measure out just a liter of water. Well, they had lots of techniques by measuring buoyancy, but it just was not such an easy thing to do. And so they did what people have done again and again and again. They made an artifact. They made a cylinder of platinum that was as close as they could make it to the mass of a liter of water. And here is that cylinder of platinum. I'm holding the actual kilogram of the archives, deposited in the archives in the same year as the meter of the archives was deposited. That cylinder of platinum is equal to the mass, as close as people could make it at the time, to the mass of 1 liter of water. And a few decades later, as a result of the International Treaty of the Meter, they made another version of this out of an alloy of platinum and iridium, and the mass of that object was chosen to be as close as possible, that it was manufactured to be as close as possible to the kilogram of the archives, and that became the new kilogram. Now, think about this. We are now in the 21st century. The unit of mass is defined in terms of an artifact that was made in the 19th century, in the late 1800s, that was based on an object that was made in the 18th century. Well, that's really a scandal that we should have such an antique way of defining mass. I mean, after all, if someone were to leave a fingerprint on the international prototype of the kilogram, all of us would lose weight. Well, nobody has left a fingerprint on the international prototype of the kilogram, but its mass is changing nevertheless. Here is a plot of a number of copies of the kilogram that were made at the same time as the international prototype of the kilogram. There was nothing special about that one. It's just that its mass was closest to the mass of the kilogram of the archives. And this shows how the mass of all of those kilograms has been drifting relative to the international prototype of the kilogram. Now, When you see all of these things drifting in the same direction, you might get the idea that maybe it's the kilogram, the international prototype of the kilogram, that's the thing that's changing. But it can't, because by law, the international prototype of the kilogram is a mass equal to 1 kilogram. Well, this is an intolerable situation. We have to fix this problem. It's sort of like defining the second according to the rotation of the Earth when you know that the rotation of the Earth is changing. We know, or at least we suspect very strongly, that the mass of the international prototype of the kilogram is changing, but there's really no way we can tell. So we need a new definition of the kilogram. And we want to do it in this beautiful way that we redefine the meter, namely by defining a constant of nature. Well, what is that constant of nature going to be? It was C for the meter. What are we going to use for the kilogram? Well, to understand that, I want to remind you of what is probably the most famous equation in history, namely E equals mc squared. What does this mean? It means that the energy of an object at rest is equal to the mass of that object times the square of the speed of light. Okay, great equation. Now here's another one. E equals h times the frequency, f. This says that the energy of a photon, a particle of light, is equal to some constant of nature, namely Planck's constant, times the frequency of the light. Now, this is wonderful. We know how to measure frequencies. We know we've defined the speed of light. Let's set these two equations equal to each other and solve for the mass. What it tells you is that the mass is equal to Planck's constant times the frequency divided by c squared. What does this mean? It means if I've got some object and it emits one photon of frequency f, and we measure that frequency, if we multiply that frequency by Planck's constant, and we divide it by the square of the speed of light, and of course we've defined the speed of light, and I'm now proposing that we should define Planck's constant, that gives you the mass change of that object. Now, we don't actually weigh photons. We can, it's just that we can't do it well enough. But fortunately, there was a brilliant idea from this guy, Brian Kibble, who came up with what we now call the Kibble balance or the Watt balance that allows us to use Planck's constant to define the kilogram. So here's how it works. Let me just run this movie. And now what I want to do is to invite you to recall how we weigh things. If I've got an unknown mass here, the way that I weigh it, and you've all done this sort of thing, is I put known masses on the other side of the balance until it balances. And when the known masses balance out the unknown mass, then I know what the unknown mass is. It's equal to the sum of all the weights here on this other side. Well, that's great. But it doesn't solve the problem because these known masses all have to be calibrated in terms of the international prototype of the kilogram. But imagine a different way of doing this. Let's say that I replace this stack of known masses with a coil of wire. And that coil of wire is immersed in a magnetic field, and I put current through that coil. And because of the way the current interacts with the magnetic field, it produces an electromagnetic force, and I can adjust this current until it balances the gravitational force of the unknown mass on the other side. Now, if I knew where all these wires were, and if I knew what the magnetic field was everywhere where the wires are, and if I knew how much current I put into the wire, then I could measure this mass based on the definition of the ampere, which has to do with the forces created between current carrying wires. The trouble is, I don't know how to make those measurements on the magnetic field and on where all the wires are, because it's just too hard to know where the current is flowing in the wires, and I've got multiple layers of the wires, so it's hard to measure them. So here's where the genius of Kibble comes in. What Kibble says is, great, let's do a different kind of experiment. Let's take that same coil of wire, immersed in the same magnetic field, and now let's take the leads of that coil of wire, and let's connect those leads to a voltmeter. And now when I move the coil, it's going to generate a voltage, because if you move a coil in a magnetic field, it generates a voltage. This is how generators work. And if I measure that voltage, and if I measure the velocity at which the coil is moving, it gives me all the information that I need about the geometry of the system and the strength of the magnetic fields. Everything else cancels out. So here's what happens. I get the mass that was from the weighing part of the experiment. You see, there's two different parts of the experiment. There's the weighing, and then there's this velocity mode where I measure the voltage. Well, during the weighing part, I've got the mass, I've got the acceleration of gravity, that gives me the force. I multiply that by the velocity from the other experiment. And that's got to be equal to the current that I did in the weighing mode to balance out the gravitational force of this mass. That current times the voltage that I get from the velocity mode. So each one of these sides of the equation has something from the weighing mode and something from the velocity mode. And the two things have to be equal, because mg times v is the mechanical power, and I times v, where v is the voltage now, is electrical power. And in a proper system of units, mechanical power has to equal electrical power. And so I solve for m, and that gives me what the mass is in terms of the current, the voltage, and the velocity. Now you might say, wait a minute, where does Planck's constant comes in? And that's because of the way in which we measure the current and the voltage. And I'm going to breeze through this kind of quickly, but the modern way in which we measure voltage and current is using something called the Josephson effect and the quantum Hall effect. The Josephson effect, here's Brian Josephson, and the quantum Hall effect, there's Klaus von Klitzing, who discovered the quantum Hall effect. They give us a way of measuring voltage and measuring resistance in terms of constants of nature. So the voltage is proportional to Planck's constant divided by twice the charge of the electron, and the current is gotten by using a resistance that's measured in terms of h over E squared, and then you measure the voltage across that resistance, which is measured in terms of h over 2E, and the E's cancel out, and the mass is proportional to Planck's constant. So that's where Planck's constant comes in. Okay, here's a picture of the Kibble balance that we use to do this at NIST. So on one side of this wheel, there's a strap that goes over the wheel, and hanging down is a coil in which we can put current. And on the other side is an activator that can move it to any position we want, and can move it at a constant velocity. And this thing can give us a kilogram that is good to about a part in 10 to the eighth, which is better than the changes that we were seeing from year to year due to, well, we don't really know what they were due to. We assume some kind of dirt is going on or going off some of the kilograms, but we can't really tell because we had nothing to compare those kilograms to. Now we have something, the Kibble balance. And the people who did this at NIST were so confident that they tattooed the values of the fundamental constants onto their arms. These people are really serious about metrology, just like those ancient Egyptians. Well, here are a few questions that you might want to think about having to do with mass. But before we go on, I want to show you another really cool way of getting mass by defining Planck's constant. You see, all we're going to do is we're going to define Planck's constant. We're not going to say you got to use a Kibble balance, because you don't. Once you define Planck's constant, then in principle, you define what you mean by a kilogram. And here's another way of doing it. Imagine I have an atom. This is typically a rubidium atom. And I shine in light that is capable of taking the rubidium atom from its electronic ground state to some electronic excited state by absorbing the energy of the photon. But the photon is also carrying momentum. So when the photon is absorbed by this rubidium atom, not only does the electron go to an excited state, the whole atom recoils, and it recoils with a velocity that's just given by momentum conservation. The new momentum of this thing, which is its atomic mass times its velocity, has got to be equal to the momentum of the photon, which is Planck's constant divided by its wavelength. Well, I can measure the wavelength really well. I'm going to define Planck's constant. I can measure the velocity of the atom using a technique called atom interferometry, but that's not really important. It can be done really, really well. And what that means is that if I solve this equation for the mass, it means that I know what the mass of this atom is once I've measured the velocity and measured the wavelength of the light and fixed the value of Planck's constant. I know the mass of that atom in kilograms, not in some funny units like atomic mass units. I know what it is in kilograms. And then all I've got to do is multiply up so that I've got something that's a big enough mass that I can just use it in a practical way. Well, people have made a sphere of silicon. Here's a picture of it. And that sphere of silicon is the most round object that has ever been made. It's out of round by maybe a couple tens of nanometers, a billionth of a meter. It is just an amazingly beautiful, isotopically pure silicon. And then you measure what the distance between the silicon atoms is in this perfect crystal that has been polished into a sphere. And that means if you measure the spacing between the atoms, and then you measure the size of this sphere, which they do very carefully, you know how many atoms are in there. And since you know what the mass of one atom, and then you just compares silicon to rubidium at very high precision, you know what the mass of this object is. It's not an artifact because anybody can make another one without any reference to this object at all. All they have to do is to make the right measurements on the silicon and the right measurements on the rubidium, and everything is fine. And this is another way of getting a kilogram by using Planck's constant. So people all over the world were using both of these methods, the Kibble balance method, the electromagnetic way of getting a kilogram, and the silicon sphere way. And when they all agreed to the desired amount, a couple of parts in 10 to the 8th, they changed the definition of the kilogram. And in Versailles in 2018, the General Conference on Weights and Measures decided to redefine the kilogram with the definition to take place the following May. And here's the video.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world scientific community.
At times, it seemed
Impossible.
accurate.
Precise measurements.
Anytime.
Anywhere. But
We did it.
Ce l'abbiamo fatta.
We have no special. Lo logramos.
那些玻璃
我们做到了。
Biz buna nail olduk.
Proud om daar.
We worden chassade. Het is ons gelukt.
We сделали это.
Fantasma.
Vi gjorde det.
Amerika.
Mi smo to učinili.
Dokázali jsme to.
سويناها.
Congratulations. 축하합니다. Felicitaciones.
Mazal tov.
Congratulazioni.
Shatera le lavorisha.
Selamat sukses.
Parabéns.
Ongela. Omedeto.
Amguida.
Onneksi olkoon.
Mabruk.
Kapai.
Aiko.
Félicitations. Congratulations.
So 60 countries from all over the world, members of the
It took more.
the General Conference on Weights and Measures and signatories of the Treaty and the Meteor agreed unanimously to redefine the international system of units to have a different definition of the kilogram, and for that matter, a different definition of the ampere. It used to be that the ampere was the current, which in two infinitely long straight wires a meter apart would produce a force of 2 times 10 to the minus 7 newtons per meter of length. Well, that's no longer the case. Today, the ampere is defined by defining the charge of the electron to be a certain number of coulombs. And since an ampere is a coulomb per second, that means that under the new definition, that the ampere is a certain number of electrons per second. So that means that we've defined both Planck's constant and the charge on the electron, which means that the Josephson constant, the thing that allows us to measure voltage, and the von Klitzing constant, the thing that allows us to measure resistance, now become exact. and we can use them to do all of our electrical measurements. Well, that's not all. The mole, the amount of substance, used to be the number of entities equal to the number of carbon-12 atoms and 12 grams of carbon-12. Now it's just a number. We have defined the Avogadro constant, or Avogadro's number, to be a certain exact number of entities per mole. So we now say that a mole is this number of a mole of anything. Let's say a mole of cesium atoms is going to be this number of cesium atoms. The Kelvin, which was the unit of and is the unit of thermodynamic temperature, used to be defined in terms of the triple point of water. That is 1/273.16 of the triple point of water was the definition of what we mean by a Kelvin. In other words, we've defined the temperature of the triple point of water. Well, now we have a new definition. We're defining what Boltzmann's constant is. So Boltzmann's constant tells you how much energy, how much thermal energy is contained in one of the elementary constituents of, say, a gas at a certain temperature. The equipartition theorem tells you that 1/2 kT, where K is Boltzmann's constant and T is the temperature, that's the kinetic energy of motion along one particular direction in a gas of atoms. So that's a new way of measuring temperature. And what it means is we now have a microscopic understanding of what we mean by temperature. Namely, it's the kinetic energy of the atomic constituents instead of a macroscopic understanding that says that it's a certain fraction of the temperature when we have a certain phase transition. And so the French Revolution brought us this metric system, which was later defined to be the International System of Units. The International Treaty of the Meter gave us an agreement worldwide about the adoption of these units. And on the 20th of May, 2019, the anniversary of the signing of the International Treaty of the Meter, we had the biggest revolution of units since the French Revolution. We now have all the base units, as I promised you, defined in terms of some fundamental constant. So here's the set of fundamental constants, and there's the set of units, and that's the new SI, the new International System of Units, the new metric system. We have, it seems, finally realized the dream that the French revolutionaries had, to have a system of units that will be good for all time and for all people, except perhaps time itself. Because you see, right now our definition of time is based on defining what the frequency is for a transition in the cesium atom. And the trouble is that we've found better atoms. The cesium atom is not going to get much better than about a part in 10 to the 16 because it's got all kinds of problems. We now have better atoms, strontium, terbium, aluminum ions, that have much higher precision, that allow us to build atomic clocks that are far more precise than what the cesium atomic clock is. Today, the definition of the second is still what's given right here, that this is the frequency of the cesium atom. But right now, the international community is discussing how to change that definition. And I'm guessing that sometime within the next decade, we will have decided upon a new definition for the second. And so, will that be the final definition? Who knows? Because we might find still a better atom to make a better atomic clock, or maybe even a nucleus to make a kind of a nuclear clock. And so, for the future of time, only time will tell. But we've come to the end of the time for this lecture, and I thank you very much for your attention, and I'll offer a few more questions that you might want to think about as inspiring some of your own questions about the nature of measurement and this reform of the International System of Units. Back to you, Colin.
Great. Thanks, Dr. Phillips. I think we're ready to start questions. So for everyone in the audience that's interested to ask one, you can use that Q&A button on the bottom. And we'll just go ahead and start kick it off here with the first one that's been submitted. It says, are the constants used for measurement, such as Planck, still changing?
Yeah. So the answer is no, because it's the law. They can't change.
Yeah.
Now, you might say, well, what does that mean? Well, what it means is that we've made this decision that we're going to use a fixed value that will never change by law, as the definition of a meter. Now, if you could imagine that something like Planck's constant did change, and I don't even know what that would mean, okay, because in fact, I don't think it's even meaningful to say that Planck's constant changes in time, then what that would mean is that you've changed what you mean by a kilogram. But in fact, there's a very good argument that says that it doesn't make any sense to think of Planck's constant changing, which in a certain sense, you can see why. If you can define it by defining your unit, then it really doesn't make much sense to think of changing it. We could decide we wanted a different definition of the kilogram, but why would we do that? That would be silly.
True. That's great. There's actually a question that sort of relates to that. I'll just read off here. It says, how do these constants relate to measuring or quantifying gravitational waves moving through space in this planet?
Yeah. Well, the answer is today, not much. Gravitational waves are so weak that we're really not going to see their effect on these kinds of measurements, but in principle they could, for the following reason. Let's take the definition of time, the second. We know, according to Einstein's theory of gravity, the theory of general relativity, that a clock will tick at a different rate depending upon where it is in the gravitational potential. So when we say that the ticking rate of a cesium atom is a certain frequency, what we really mean is that it's a certain frequency at a certain place in the Earth's gravitational field, which we decide, just for convenience, to be the level of mean sea level. Now, this is problematic, quite apart from the question that was asked, which I'll get to in a moment. This is problematic because of the fact that sea level is changing because of global warming. So the actual definition is difficult. Now, it's not a problem yet because the definition is based on cesium, and we would have to change the cesium clock by 1 meter in height in order to get a part in 10 to the 16, and it's not quite good to a part in 10 to the 16. But the new clocks are going to be good to a part in 10 to the 18 or better, and that means 1 centimeter. And the sea level is definitely changing by that much, and so people are thinking about how to get around this. But now to return to the question, if a gravity wave goes by, it changes the gravitational potential. So that's going to change the frequency of the cesium clock. So somehow or other, you've got to have a way of taking that into account if you want to use it as a very good clock. And people are already doing that. Forget gravity waves, just the fact that the Earth going around the sun changes its distance to the sun means the total gravitational potential changes. Jupiter changes its position relative to the Earth. And so we have to take into account Jupiter as well as the other planets. And in order to make really good measurements of time, say to time millisecond pulsars that come from practically the other side of the universe, we have to make these corrections. For any measurement that's local, we don't care. But as long as we make all the measurements at the same time, that's where a gravity wave might come in. You don't want to do part of your measurement when a gravity wave is going by and another one some other time. But fortunately, we don't get gravity waves come by that often. So, and we're not sensitive enough yet that gravity waves are important, but in principle, yes, we would have to worry about those things, and we'd have to take proper measures to make sure we were measuring the right thing.
Makes sense. That's a great explanation. I have another question here that says, this is fantastic, Dr. Phillips. Is it my understanding correct that a number of the units, perhaps with the exception of the mole, ultimately rely on the definition of the second?
Yeah, that's right. In fact, you might think of there being a kind of a hierarchy. First, you define the second, then you define the meter as being how far light travels in a second. You had to define the second to do that, or what the fraction of a second is that the light travels to make a meter. So you wouldn't have been able to give that definition until you gave the definition of the second. In the same way, Planck's constant, which has the units of joules second, you couldn't talk about it in terms of its units unless you knew what a second was. And you have to know what a meter is too, because a joule has units of length as well as units of mass and time. So yes, you have this hierarchy, but for for almost everything. But as was pointed out, you don't need that for the mole. You don't need that for the candela either, but you do need it for the Kelvin, at least the way it's defined now, because Boltzmann's constant has the units of joules per Kelvin. So you got that joules in there. So you need the second and the meter and the kilogram in order to define what you mean by a Kelvin. So yes, it's sort of built up from the start.
Yeah. That makes sense. And there's actually a question that actually touches on what you mentioned, which is, could you please speak briefly about the definition of the candela?
I'd actually rather not, because the candela is a little bit weird in the following way. The thing that we've set as a constant of nature isn't really a constant of nature. It's the conversion between optical power, a certain number of watts per square meter, and the way the human eye perceives brightness. Now, the saving grace is that most people perceive brightness in the same way. You go all over the world and you ask people from all different places and backgrounds, how bright does this look compared to this reference brightness that we can set, by having a certain amount of light of a certain color that we measure. And then you say, how does this light of a different color, how does it compare? And that's how they figure out what this constant is. And fortunately, people don't vary that much. And it gives us a way of defining what we mean by a candela or a lumen, which is more like total light output. And why do we want to do that? So that we can sell light bulbs to people and they'll know how bright they are. And that's what matters, is how bright it looks to you. So that's what the candela is about. It's about how bright things look to the human eye. So not exactly fundamental, but apparently at least a constant, maybe not of nature, but of human biology here on the Earth.
That's what I was going to say. It's the human perception is all like pretty relatively the same, which is pretty wild to think, because we're supposed to have all these different unique experiences, but this somehow that's super, super interesting.
But we are genetically so similar across the whole world. In fact, within any given population, something like 70% of all the genetic diversity that you have throughout the entire world is already contained in any given population. So we really are all related very, very closely.
That is wild. Yeah. Another question coming back to this, the meter and fundamental constants. It says, since we already have a definition of the meter using a fundamental constant and we know the value of the speed of light, couldn't we define the second as the amount of time it takes light to travel 299,792,004, the big number meters?
Well, then you'd have to have a separate definition of the meter, because the current definition of the meter involves the second. So if you wanted to turn it around, then you could have, but you wouldn't want to, you could have said the meter is the distance between these two scratches. And then you could make a second by defining how long it takes light to go from one scratch to the other. You see, you'd need a separate definition of the meter, which you could have done by the wavelength of light, but it seemed more convenient to start with the second, in part because time is the thing we measure best. Of all of the things that we measure, frequency, and time is just the inverse of frequency, is the thing we measure best. So why not use it as the thing to start with?
Yeah, no, that's great explanation. See some more questions coming in. We're working our way down the list here. It says, what will be the next dimension where metric will be set up from your standpoint? Do you think it will be applied to computer sciences or artificial intelligence? Thanks.
Yeah, well, I'm not entirely sure I understand the question, but I'll try to answer it. We are in the midst right now of trying to understand how we should apply these general principles of measurements and units of measure for things that have to do with computers. In other words, things like the size of the memory of something. Well, that seems sort of obvious. You know, we measure that in bits or bytes. But as you probably know, the thing that's called a kilobyte isn't really 1,000 bytes. It's 1024 bytes. So codifying all of that. And then another thing that comes in is, what about how many pixels you have, say, in a camera's storage? Well, how am I going to quantify the pixels? Should I do it in terms of the area that those pixels cover? What about the spacing between them? I mean, these are all things that we can understand in principle, but they haven't yet been codified. And so we're working on ideas of how we can give clear, consistent, and useful definitions of all of these things that everyone will finally agree on. Because at the moment, we don't have final agreement on some of these ideas.
Yeah,
I'm not sure if that really addresses the question, but
I think it does. Yeah, it's just it's somewhere we're still exploring, and we're making our way to that. I think another question we have here, it says, when would it matter if the gravity wave altered the measurement of time or distance?
Well, let's say that you were comparing the frequency of two different transitions, and you had some theory that told you what that ratio should be. If you measured one of them when a gravity wave was going by and another one when it wasn't, then that might represent a problem. But now that I think about it, because the gravity waves are so broad over space, they would be affecting the thing you're measuring in the same way that they would affect the reference. And so maybe it wouldn't really make any difference. I have to think about it a little bit more carefully. But it could be that as long as you don't try to compare things that are outside of the gravity wave, that maybe it would be okay. So I'm not really sure, but I'd have to think about that more carefully.
Oh, that's great. Another question here that says, all the kilogram artifacts increased with time. Could that be that is the reality due to the universe expansion?
Well, it's hard to see why they should be different because all those artifacts were made at the same time in the same way. So obviously something about them was different. They had slightly different masses, but that we don't think that makes a difference in how they change. But somehow or other, there must have been something. Maybe there was inclusions in one of them that weren't in the other, but it doesn't appear that it's something so fundamental. And there's no good reason to believe that it should be something fundamental, because these are relative changes of things that are nominally identical. So why would something having to do with the expansion of the universe affect one of them differently than the other when nominally they're the same?
Yeah. Wow, that's great. A couple more questions here coming up. One that says, can you comment on the leap second?
Yeah. Okay, so remember, the old definition of the second was based on the mean solar day. Now, Uh, uh, the trouble is that, as we mentioned, that the rotation of the Earth is not constant, and so knowing what time it is based on a rotation of the Earth is not going to be the same as knowing what time it is using atomic clocks, which don't have that feature. So people are keeping track of the rotation of the Earth relative to the atomic clock, and whenever they get out of sync, which they do from time to time, by 9/10 of a second, then you've got to reset your time so that you don't end up with it being noon in Greenwich at a time when the sun is not highest in the sky. Now, I say that sort of in a flip way. The fact is that I would keep saying mean solar day. The solar day changes during the year because of a combination of the ellipticity of the orbit, as well as the inclination of the Earth's axis. That means the time, the apparent time between transits of the sun varies throughout the year, and sometimes your sun clock could be off by as much as 15 minutes compared to an atomic clock. But now if you average it over the whole year, that goes away, except for these things having to do with the tides and the ocean currents and that sort of thing. And that's where the leap seconds come in. When the rotation of the Earth gets out of sync by, something close to a second, then we're required to reset things. And you may have even heard, I forget the last time it was done, that when it gets to be midnight on New Year's Eve, in the time zone for what's called universal coordinated time, it's pretty much the same as Greenwich Mean Time, but then what will happen is that they will either go from 23:59, 59 or 58 directly to 24:00, or they will pause for a second on 24:00, depending upon whether the leap second has to go in positively or negatively. It turns out we've only had leap seconds in the positive direction, by which I mean the day has always been longer than it was supposed to be according to atomic time. So what happens is that on that New Year's Eve, you get an extra second.
Wow, that's bizarre. I've never heard that before.
Now, there's a big discussion whether we should keep doing this.
Yeah.
It's a discontinuous change. So you can imagine discontinuous changes aren't good for systems that are trying to keep track of what's going on.
Yeah.
So if the electric grid, something goes wrong on the electric grid, we want to know what's going on relative to the 60 cycles phase of the AC current in the electric grid. And if all of a sudden, you're off by a second, then that could wreak havoc if you don't take account of it properly.
Yeah. Wow. That's fantastic. I got a couple more questions. I have one here that says, can you measure the entanglement characteristics of entangled photons and describe the application to atomic time standards?
Right. So entanglement is now being used, and I'll say in a moment what entanglement means, to make better clocks. But it's entanglement of the atoms that are used for the atomic time standards rather than entanglement of the photons that are used to interrogate those atoms. So what do we mean by entanglement? As I'm guessing a lot of the listeners know, when you measure a quantum object, you can't necessarily predict what the result is going to be. So let's say, for example, that we've got a cesium atom, and it could be in one of two different states, with the electron spin pointing up or the electron spin pointing down relative to the nucleus. That's an oversimplification, but let's not worry about that for the moment. You could prepare the atom so the spin was pointing up, and when you measured it, you'd find that the spin was pointing up. Same thing if you prepare the atom with the spin pointing down. But you can also prepare the atom in what we call a superposition, where in a certain sense, it's both up and down at the same time.
Yep.
We know how to do that. We know how to do it very accurately. But if you now measure whether it's up or down, there's no way you can predict whether it'll be up or down, but it'll be one of the two, because that's what you're measuring. Is it up or down? And you're going to get an answer, whether it's up or down, but there's no way of predicting that. Okay.
Wow.
That's why one of the reasons why Einstein didn't like quantum mechanics. He said, I cannot believe that God plays at dice with the universe, that it could be a completely random process whether the thing is going to be up or down. But as far as we know, it is. And Einstein was wrong about this. But one of the reasons why we know Einstein was wrong was because of what I'm going to say next about entanglement. Let's say that I've got two cesium atoms, and I prepare it in a state where one of them is up and one of them is down. And when I measure this one, I'll get up, and when I measure this one, I'll get down. Fine, no problem. Now let's say that I prepare it in a state where the one cesium atom is up and the other one is down, in a superposition with that first cesium atom being down and the second one being up. That's what we call an entangled state. If I measure one cesium atom, I have no way of predicting what the result is going to be, up or down. But once I've measured one of them, I know what the other one's going to be.
Yeah.
That's what we mean by entanglement, that the uncertain fate of the atom when we measure it is entangled with the fate of the other atom when we measure it. Now, for reasons that I don't want to go into, if you do that entanglement among your cesium atoms or your strontium atoms or whatever in the right way, you can do better than what you would do if you didn't entangle them. So let's say that I've got 1 million cesium atoms, which is pretty typical for these atomic clocks. 1 million is not a very big number, by the way. If you had a speck of something that had 1 million atoms in it, you would not be able to see it. It would just be too small. But anyway, that's a typical thing. If you could entangle those atoms in the right way, you could, well, first of all, let's forget about the entanglement for a moment. Let's say I've got 1 million atoms. I can do 1,000 times better than if I only had one atom. So that's pretty good, right? But it's the square root of the number of atoms. And that's because of this random nature of the way measurements are. That when I do more and more measurements, I get more and more precision, but it only increases like the square root of the number of measurements that I make. Well, if you were clever enough to do just the right kind of entanglement and the right kind of measurement, you could make the measurement improve by another factor of 1,000. In other words, it would get better not as the square root of the number of atoms, but as the actual number of atoms. So that could be a pretty big deal, even if you only have a few thousand atoms. And that's what people are working on now, is to entangle the atoms in such a way as to get a more precise measurement than you would get if you didn't entangle them. And so this is going to make it easier to operate the atomic clocks. You won't have to average for as long. This is really in its infancy right now, but it's certainly something that's happening.
That's great. Thanks. Another question here, it says, is there an SI unit of radioactivity? If there is it derived unit or a base unit? If it is a base unit, what is the fundamental constant it is based on?
Yeah, so it's a derived unit. So first of all, I should say, what is a derived unit? You saw the base units. Everything else in the SI is a derived unit. So for example, we don't have a name for it, but velocity is meters per second. We have to use 2 of the base units in order to have have a unit for velocity. There's other things that do have names, like the joule. So the joule, see if I can remember what it is a kilogram meter squared per second squared. So that's a derived unit. Okay.
Yeah.
There are units for radioactivity, and without looking up in the handbook, the SI handbook, I can't remember which is which and what it means, but there are things called grays and sieberts, and these have to do with how many radioactive decays per second you have. And so these are derived units based mainly on the second, but it's not the same as a second, it's an inverse second, but then there's this other feature that it only refers to radioactivity. It doesn't refer to other kinds of things that might happen. So it's kind of a funny definition, but we consider it to be a derived unit, and it is within the international system of units, if I'm remembering correctly.
Oh, that's great. And there's actually
I have
another question.
an SI brochure handy so I can check these things out.
Yeah. Another question, actually, somewhat related to that, says, in general, is it at all problematic to define these units somewhat recursively, e.g., the meter being defined based on the second?
Yeah, no, I don't think there's any problem in defining those things like that, as long as you keep track of what you're doing. The fact is that the modern way that we'd like to do it is, instead of saying the second is this, and then the meter is this using the definition of the second, what we'd like to say is, here's these 7 numbers. The SI is the system in which those 7 numbers have the values that we've decided upon. So when you do it that way, you don't give priority to any one of the units. Everything is sort of on an equal footing.
Yeah.
And that's a very appealing approach that some of us are trying to promote.
Terrific. I think we got one more question here, and then we can kind of wrap up. I know it's getting late for you over there, Dr. Phillips, so we'll respect that time, and we'll finish with this one. It says, are there any possible physics theories which might reduce the number of constants?
Okay. Now this is an important question, because it's not so much a matter of physics of how many constants we have. It's a matter of choice and convenience. So let me give you an example. We could, if we wanted to, not have a unit of length called meters and just use seconds to define length. Well, how would we do that? Well, we would say that, we use the same definition of second as we've got now, and then we would say that distance, which is about 30 centimeters, is 1 nanosecond. Now, we're actually used to doing this all the time. People say, how far is it to the university? And you say 10 minutes.
Yeah.
We all know what that means. It means that's how long it would take if you got on your bicycle or get in your car or whatever, however you're sort of assuming your mode of transportation, because we know about how fast those things are. Well, we could use the same reasoning for light, where we know exactly what it means, and we know that it's consistent, and we could say the distance from here to here is 1 nanosecond. Then I don't need another unit like meters. Meter is now about 3 nanoseconds.
Yeah.
The question is, do you want to do that? For example, we have Kelvin for temperature. We could have easily defined temperature in joules instead of in kelvins. So you'd say, well, how hot is it today? Well, feels to me like, a few times 10 to the minus 22 joule. Okay, probably not very convenient, right?
Yeah.
So, but we could. I mean, nothing in physics prevents us from using energy as a measure of temperature, but it's not convenient. And also, there was historical reasons. I mean, before people understood what temperature was, they came up with names, like Celsius degrees and Fahrenheit degrees and kelvins. Even now that we understand what the microscopic origin of temperature is, it's a lot more convenient to have kelvins rather than joules as our measurement of temperature.
No, that totally makes sense. Yeah, that's a great question.
We didn't have to make moles a base unit. We didn't have to make the candela a base unit, but it was convenient to do so. And so the question of how many units we have is really a matter of what we've decided as a society is the is going to make life easiest.
Yeah, no, that makes a lot of sense. Thanks for explaining that. So I think we'll wrap up here. So thank you everyone in the audience for tuning in this evening. And thank you so much, Dr. Phillips, again, for taking the time to speak with us tonight. This topic was super fascinating, I think, for all of our attendees, and they definitely found it interesting. They were asking all these questions. So this was awesome. Again, thank you. For our audience members, we will be doing another Cafe Sci next month. So be on the lookout in your inbox for that invite. With that, have a great rest of your Thursday. I look forward to seeing you all next month, and I'll let Armand, our Cafe Sci lead, hop on and give a big warm thank you to our guest speaker this evening.
Yeah, this was absolutely fascinating, Dr. Phillips. Thank you so much for being with us today. It was such an honor to have you.
It's been a pleasure to be with you, and a pleasure to engage with all of your audience members with these fantastic questions. This has just been lovely.
Absolutely.
Absolutely. All right, everyone, have
Thank
a
you,
great rest of your
everyone, for
Thursday.
joining.
Take care.
Have a good night.
Bye-bye.
So long.